This is a video about math functions. What's a function anyway? And it'll be my first video about math. And so it'll be pretty simple functions we're talking about today. The simplest function actually is not much of a function at all. It's say y equals a constant. Y equals c. C is a constant under certain circumstances, let's say. So what does a constant function look like? Let's say this is x and this is y and this is the value of c. No matter what x is, c stays the same. The value y equals c. That's a constant function. That could represent, for example, the weight of an object, W. W turns out is equal to the mass of the object times this constant, gravitational constant we call G. So G, I don't know, something like 32 point something feet per second squared. It's in that's an acceleration units. Its weight can be confusing because we generally weigh things in pounds, but the British unit for mass is not pounds at all. It's a very confusing thing, but we all understand that our weight is the same as long as we measure it on Earth. But so it's W equals mg. M is constant, G is constant. It's going to look just like this other function that I drew. It's going to be constant. Kind of boring, actually, right? But as it turns out, we know, in fact, that our weight is less if we are on the moon. Why is that? Well, it turns out that little g is not really a constant unless we're at the same altitude from the Earth constantly. And if we, say, go into space, we know we'll be weightless. G will be 0 if we're far enough away from other heavy objects. So to say something is constant, we need to stipulate the circumstances under which something is considered to be constant. And in this case, we would say, well, as long as we're on the surface of the Earth, approximately, and we don't go up any really tall mountains, then our weight will be constant. We'll measure the same on a hill as we do, at sea level. But if we go into space, our weight will be 0. So it's not totally constant, but under certain circumstances, it can be considered constant. So we have to stipulate that. So let's consider another case. Let's consider a car moving at constant velocity or constant speed. We usually write that down. Well, a couple ways to write it, but for today, let me write d. The distance traveled by the car is equal to the speed or velocity, we'll call it v, times the time. Okay, so when the clock starts at time equals 0, maybe we have a stopwatch or something, uh, the velocity doesn't matter because our distance traveled is 0. Um, let's say if the constant v is 60 miles per hour, we know that within 30 minutes d will be 30. So let's draw that. D, distance traveled over time, is going to increase with time, right? And when time equals 30 minutes, D will be 30 miles, if D is in miles. So we would draw it like that. Even though velocity itself is constant. So velocity, in this case, is always 60. Looks like that. Hopefully that makes sense so far. Now, this seems a little bit strange though. Velocity goes from 0, let's say before you start the clock, it's 0, and at time equals 0, it suddenly jumps to 60. How does that happen? We know the car has mass, and it can't actually go from 0 to 60 in no time at all. In fact, normally it takes a few seconds for your car to get to 60 miles an hour, even if you put your pedal to the metal and floor it. So what's going on? How can we even draw it like this? Well, it's an approximation that we make in the case where we're wondering how long is it going to take to get somewhere. Approximately. We don't always need to know exactly how long it's going to take. So we know in fact that it takes a few seconds to gain speed in a car. But if all we want to know is how far we're traveling over, several hours, that little bit of time really doesn't matter much. It's insignificant. On the other hand, if we were to be watching drag races, which only last, a few seconds, then those few seconds where you're accelerating are actually very important in determining the outcome of the race. So again, even in this case, it's not as simple as it seems. We have to stipulate that this is an approximation, or we call it an idealization, because this actually should look more like this, right? It should take a little bit of time to get up to that speed, but we're idealizing, we're approximating with this function. So we're talking about approximating and idealizing functions with these kind of step changes. Let's add a little bit more physics to our discussion, and think about this. A golf ball and a golfer putting a golf ball on the surface of a putting green. Let's say it's a level putting green, and so we could say that it's pretty instant that the ball is first stopped and then suddenly has a constant velocity or near constant velocity, at least for a little while, until it slows down. When it gets near the hole, hopefully it's going to slow down, right? So that's kind of the planning that the golfer does. But what's happening on the putting green is the putter is imparting a impact, or what we call an impulse, to the ball. The putter imparts an impulse that causes the ball to suddenly have speed. But again, in reality, since the ball does have mass, just like the car does, maybe not as much, it can't have speed instantly. That just defies the laws of physics. And the impulse actually acts very quickly. It doesn't take several seconds, it takes a fraction of a second. But it does take time, because that's the physics. It's anything that has mass requires some time to attain a velocity, to gain momentum. Force has to act over time. It can be a very short time, but still some time nonetheless. Does the golfer really care how long the impulse is between when, during which the putter is smacking the ball? No, he doesn't care. What he cares about is that he gives it the right amount of impulse in the right direction. So those are the things that matter in that case. So again, this idealization that we used before would be fine also with the golf ball, but now we have a little more understanding of how things could be idealized in this way and still have a good representation as something going from 0 to a constant velocity in 0 time, or a very small amount of time that's negligible. Okay, now that we understand that, let's consider changing our function. Let's consider a case where, let me draw another velocity versus time. Let's say after 1 hour, so the velocity was 60. Let's say suddenly at an hour, the driver slams on the brakes and starts going 50. So if this was 60 miles an hour, here now, if I look over here, it's going to be 50 miles an hour. He suddenly jams on the brakes. And yes, the time between when he steps on the brakes and when he comes down from 60 to 50 is not 0. It might be a second or two. It's not 0, but we're gonna idealize it that way. So if we do that, this function is still a function, but it's called piecewise continuous. This is considered a discontinuity in time at the time 1 hour, but it's piecewise continuous because it picks up there and goes on, and it's only discontinuous at one point in time. It could be discontinuous several times to be called piecewise continuous. But that's what that looks like. And now let's draw the D. So the D, the distance traveled versus time. Well, we know at 1 hour he's going to change speed, and he's going to have traveled how long? Well, he was going 60 miles an hour for an hour, so he's going to have traveled 60 miles within an hour. So this over here is going to be 60 miles. D is in miles. And within an hour. But then he's going to slow down at that point. And so what does that look like? Well, it looks like a different speed. And he's traveling fewer miles per hour. So let's say in 2 hours time, how far is he going to have traveled? If this is 2 hours, 2 hours here, and this is 60, but now he's going 50. So if we trace this back over here, what's it going to be? It's going to be 60 plus 50, right? Which is 110. So that's a piecewise continuous function, and this function is called a linear function, but it's only piecewise linear, because whereas this function was linear, that is, it's a line when d equals vt and v is a constant, this is a linear function. Okay, but if that's only true part of the time, and then we call this piecewise linear because it's linear part of the time, and it's a different line at a later time, and you could change it again as long as we know exactly when. In fact, we write down a piecewise continuous function. We say we would write something like v equals 60 for t less than or equal to 1 hour, and v equals 50 for t greater than or equal to 1 hour. And remember, that's an idealization again, because it's not precisely 1 hour. When he slows suddenly from 60 to 50, it's not 0 time. It takes him a second or two, but we're going to approximate it as 0 time where he decelerates, because that's good enough for the calculation. This is going to be 100 plus or minus, 10 feet or something. 110 plus or minus some small amount. So it's close enough for our purposes. Okay, I hope that makes sense. So let me tell you what's not a function at this point. So what's not a function, this is a function, this is a function. Well, let's consider distance over time as a function, and let's just say the guy's constantly changing speed, going faster, going slower, and so and he might even turn around and go back the other direction and decrease his distance from the origin over time. But what he can't do, so this is a function so far. What he can't do, this is a function. What's not a function is if I do this. If I go, whoa, whoa, what happened there? I went back in time. That's not a function. Okay, for whatever value of t I choose, a function must have a single value. If I change this is called the independent variable, and this is the dependent variable. And you can see in this function, no matter what value of time I choose, I can find the value over here of d. But in this thing that I've drawn, if I ask you about this time, what value are you going to give me? Because there's 3 different values of d at that time. It's not a function. You have to be able to give me a single value for d. I can do that here, but this one that doubles back in time, no. If I go back in time in a real function, I'm talking about tracing back on the curve of where I went, how fast I was going, how far I had traveled. I'm going back on the same line. You can't do this kind of thing and still have a function. Okay, so we understand what is not a function now. I'd like to go on to one more case, kind of conclude this video with another case of a linear function like this one. This one was piecewise linear, and I'm going to show you another function. Let's consider I have a mass, and maybe I put it on a little roller skate, and it's attached to a spring, and that spring has a constant K. So K is a constant but now I'm going to have to stipulate again, because guess what? So what is spring? The function I'm talking about is the force in the spring is equal to K times X, where K is a constant. So I draw that like this. X is the amount of stretch, and that's here. I'm sorry. I want this to be the force in the spring, and it's equal to Kx. So that's a linear function again, as long as K is a constant. Again, I have to stipulate K is a constant. When is K a constant? Because I bet if I pull this mass this way about this far, this function is going to look very different. It's not going to keep going like this, because what's going to happen? Well, at some point the spring is going to actually break or start to bend or something. A spring can't just stretch forever and ever, right? So we know that we have to bring physics back in and say K is a constant in a region. And we could call it within the design of the spring. The spring is designed for a certain amount of stretch, and if you go beyond that, then K is no longer constant. And let me give you a case where K could be constant, say, in a different region of stretch, but it would be a different constant. Let's consider the case where I hang the mass from the spring like this, and I have a gravitational pull like that. So if this mass is fairly big, it's going to stretch that spring out. Maybe not enough to bend it or break it, but if I draw again F equals Kx, well, it's already stretched a certain amount. If we go back to 0, if we say X starts here, and then I hang the weight on and it goes down to here, and then let's say I pull it some more, it goes down to here. Well, it could be that, let's call this A. Okay, so I'm going along and I'm letting the weight weigh on it, and it gets to point A here, but then the spring starts to stiffen up, so then the force increases and starts to go on this curve. Now that's a slightly different. Let's say I measure this slope and it's K1, and I measure the slope here, and it might be K2. Sorry. So that can happen. You can have a change in the constant K if you're then measuring the motion about this little point right here versus this point down here where it was just sliding on the ground, now it's hanging and the spring has already been stretched out, it might have a different constant, K2. As long as we're talking about small motions about that position A, this might be a very totally valid equation still, but it would be F equals K2 times X, whereas this F over here was K1 times X. I hope that makes sense. I'm going to leave you with that. Until our next video. Thank you. Well, as I was editing this video, I realized I made a mistake when I was talking about how the spring, once it was stretched by the weight of the mass hanging down in a gravity field, the force that you're going to pull with is it's already been pulled by the weight of the mass, which is mg, and so the additional force that you might add at this point is going to be delta F, which I call the original mg. Well, it's some additional amount, some total amount minus the mg is going to be the additional amount. And I made a mistake here when I said K2 times X, because it's actually, if this is X and X is the full amount of stretch, then the delta force, the additional force here, is not K2X, it's actually K2X minus A. It's the additional stretch from the point A. And so, and we stipulate that this equation is true when X is somewhere near 0, and this equation is true when X is close to the value A. And that's all the change, and that's the end. Thank you.